just omitted the, sorry, this thing is not showing up here. I have omitted the name, and it says, doesn't say quiz, but this would be a quiz, but it's not. So anyway, give this one a try, just number one. And we work with a friend if you need to. I'll give you a few minutes, maybe 5 minutes, and then we'll work on this together. And so I'll come around and collect the papers that the absent people didn't pick up. So sad. I guess you could always scoot over if you wanted to work together here. It's up to you, though. Yeah, either way. Here. I know you prefer to work alone, but you could always bless Eli and Hunter with your ideas and thoughts. Oh, I just remembered, I brought my stickers. I can't remember who didn't get their test until Wednesday, but if you didn't get a sticker and you want one, I have at least all the cool stickers. So. I always want to let you have an opportunity to, do the whole thing if you have the skills or you've got it all taken care of. But I also don't want to have people bored because they're like, I don't know how to go from here. So let's see how we're doing in terms of this problem. And the first step is, of course, to label this triangle in some way that you have an X somewhere and you have this thing somewhere. So you need three things. And I usually use this thing, the radical, as my guide in the sense that I know I need 9 minus x squared. And so to produce that, I'm going to need to use the 9 is going to be associated with the hypotenuse. And then the x will be on one of the legs. So here's what mine looks like, and then we can talk about why this is. So take a minute and look that over, see if it makes sense, and if it doesn't. So those are the choices I made. Technically, you could have swapped these, but just in general, usually with a substitution like this, we put x over here so that my sine of theta can be just x over 3. But this is the start. You got to get this sort of figured out, sorted out. I don't know, is any comments or questions about why such and such is the way it is? Maybe it's just too overwhelming. I don't know. Okay, well, let's see. So I've got this written over here where you can't see it. Let me just point out that now that we've got this, we can write down things like the sine of the angle, opposite over hypotenuse. And you can also write down the cosine. The cosine of this angle is adjacent over hypotenuse. So these are things that you can actually write down based on this, and this is going to take the place of our substitution. So let me show you what I actually wrote down over here. So you can see, basically, I took those two things in purple that you're familiar with, and I just rearranged them a little bit because I knew that I was going to want to solve for x and solve for this radical. So I've got 3 sine of theta is x, and 3 cosine of theta is 9 minus x. So we have those two things that are going to be the building blocks for the substitution. Now there's one thing that we still need to deal with, and that's this dx that's kind of poking over here. So let's deal with it. To get the dx, let's use the simplest thing that we can, and that's this. If you take that and do the derivative, you get this. 3 cosine of theta d theta is dx. So this is usually the case with these sorts of substitutions, is that you end up with a couple of things that both mean, like, you end up with the same substitution for dx as you do for the radical, but don't let that bother you. So anyway, that stuff, I know you're looking ahead here, but this is the next step, everything above this line. So you can ignore the stuff below that line. So there's the triangle, and there's most of my substitutions over there. So that's what I want to focus on, at least for now. We'll talk about what I did down here in a minute. So are there other issues with that stuff, those substitutions? Don't worry, we're moving down below the line here. Okay, so let's actually make those substitutions. I realize I skipped a step here, but let's talk about them. First of all, this x cubed is 3 sine of theta all cubed. So you'd have 3 cubed, which is 27, times sine cubed of theta. So that's where this sine cubed of theta came from. We'll talk about that in a sec. And then this thing, the radical, turned into 3 cosine of theta. That's where one of these 2 cosines came from. And then the dx is off the screen, but that became 3 cosine of theta as well, and that's where the other cosine came from. So in terms of the sines and the cosines, that's where they came from. And then we'll talk about the 243. So the 243, where that came from was the fact that I have 3 3s, 3 cubed, and then times another 3 times another 3. So that's 3 to the 5th. And we all know 3 to the 5th is 243. Okay, so moving on. So that's where that came from. I just took all the 3's and put them together. Then the rest of this is a little bit of rearranging and using the skills that we picked up in the previous section. So you know that you can, actually this was one of the quiz, I think I turned it back to you. I feel like this without the 243 was one of the quiz problems. So separate out one of the signs, turn the other signs, sine squared is 1 minus cosine squared. There's not an additional square here, just so you know. It's just 1 minus cosine squared times cosine squared. And then I'm going to do this substitution. The negative there has to be accounted for, and that's why this is negative. And then, of course, you change the cosine into a u, so that becomes u squared. This one also u squared. You can simplify that. That becomes u squared minus u to the fourth. Integrating that, nice polynomial. I know I'm going pretty quickly here, but I think most of this, like the polynomial stuff, is fine. Substitutions are sort of fine. But anyway, I forgot my plus c, but I have it down at the bottom. And then I have to reset. So it's like that movie Inception, where you go to a dream within a dream. This is a substitution within a substitution. So, you just have to deal with it and work your way back out of all the substitutions. So the first thing is to deal with this, and u is cosine. So I've done that. And then after that, I have to say, okay, what is cosine? Well, we had that up at the top. Cosine is this. And so I just changed that to this. And I tried to account for all of the, like cosine is the radical over 3. And so this is the radical cubed over 3 cubed, but there's an additional 3 down there. And I realized this I could clean up if I multiplied through. And this is the radical to the 5th over 3 to the 5th. So I suppose as one final step, I might multiply through and cancel out all these 3's. But that's it. This is one version of the answer. I guess I could clean it up just a bit. Why not? Yeah, let me just clean it up just a bit to make myself look like, have it look a little bit better. So I might do this. How about this? Radical 9 minus x squared to the 5th over 5 minus 3 radical 9 minus x squared to the 3rd plus c. There, that works. So if you want to know where everything ended up, the negative over there made this one negative, this one positive. That's why I switched the order. But I mean, anything like this is fine too, either one of these. Wow, that's a lot of work, isn't it? I can't imagine that I would be able to put more than one of these on an exam or a quiz and expect you to do it in a reasonable amount of time. So I'll try to, I think what I've done in the past is I ask you to just sort of set up the substitution because there's so many steps. But we'll talk about that in a week or so. Is that right? Not next week, the week after, 2 weeks from today is the next exam. Can you believe it? It's like we're going so quick. All right, well, let's move on. Let's take a look. So I have this on the PowerPoint, but you have it before you as well. You'll see that if you scroll down, well, you don't have to just look down. I have 3 problems on this fake quiz, and we did the first one. There are 2 more, and those 2 are slightly different than the one we just did. And the solution that we're going to find is going to be slightly different. So let's work on the second one, see if we can work through this. And so here's the distinction, so you can see the distinction, then I'll take your question just a sec, is up here, the radical. So all of these trig substitution problems have a radical in them like this. This one, the radical is some number minus a variable squared. This one is some number plus a variable squared. And then the third one is a variable squared minus a number. So those are the 3 flavors of these substitutions. Hayden, did you have a question? Okay. So you figured it out though? Okay, good. Anything else before we move on? Yeah, Michael? Oh, the very top line? Yeah, I just skipped this. I'll write down the step that I skipped. I'll put it down here. So it just has to do with this particular, so going from here to the cosine. So we have the integral of 3 sine of theta to the third. So that's that x cubed using the thing in the upper right corner. And then the square root of 9 minus x squared is 3 cosine of theta. And then dx, I need to scroll over a bit. Dx is 3 cosine theta d theta. So 3 cosine theta d theta. So that's what I skipped. And then if you combine, like you have 2 cosines, so that's cosine squared. You have 3 sines, so that's sine cubed. And then 3 times 3 times 3 cubed, you can do on your calculator. If my mental arithmetic is correct, is 243. Yeah, so don't let me get away with, so thank you, Michael. Don't let me get away with skipping steps and just being like, yeah, like I remember this in grad school, especially someone would like, say, they would wave their hands and say, oh, that's trivial or whatever. And I'd be like, what? I don't have to spend 2 or 3 hours to figure out that one step. But so thank you for being brave and telling me I need to show my work. Anything else before we go on? All right, so these other two, if you understand this one, I know it's a lot, it is so much. But if you understand the general form, then the next two, they really aren't too bad. You're just shifting your focus a little bit on the way you set up your triangle. So if you get your triangle correct, you're going to be fine the rest of the way. So let's go ahead and try this one. So when we see something like this radical 9 plus x squared, if I want to make a triangle, in fact, why don't you go ahead, but do it with pencil maybe. Try to make your triangle. You're going to have that thing on one of the 3 sides, and I'll even tell you what the other 2 sides are going to be. One of the sides will have a 3 on it, and one of them will have an x on it. And you want all 3 sides to fit together with the Pythagorean theorem. So take a minute, see if you can figure that out, and then I'll show you what I have. But yeah, just pencil it in, or if you have pen, do it in light, because you might do something slightly different than me. Okay, so what I would suggest you do is, because my goal is to have the sum, and I know what the Pythagorean theorem says. It says that the square of the hypotenuse of the right triangle is equal to the sum of the squares of the other 2 sides. If I put x over there on the opposite side, and then 3 on the adjacent side, then this x squared plus 3 squared would equal this side squared, which means that that side, the hypotenuse, would be 9 plus x squared, the square root. So that's the way I would do it. The one way that you could still do it and do it correctly, but be different from me, is if you put the x down here and the 3 over here. That would also be correct. However, it would be harder in the end. So I would encourage you to do it this way. So if you ever have a plus under the radical, put the x on the opposite side, put the number on the adjacent side, and then go from there. Okay, so as with the previous, notice back here, when we wrote down the trig functions, one of those trig functions equaled x over 3, the other one equaled the radical over 3. So let's do the same thing down here. So I want to know which trig function is equal to x over 3, and which of the trig functions is the radical over 3. So I'll put equals here. So see if you can, I think most of you hopefully know which trig function corresponds with x over 3. In fact, I'm so confident that I'm just going to start randomizing now. It's always fun. Let's see. All right, Ryan. Ryan, do you know what trig function is equal to x over 3? Opposite over adjacent? Yeah, tangent. Tangent is opposite over adjacent. Now, there's a problem with this one because this one is hypotenuse over adjacent. And that doesn't correspond with any of our SOHCAHTOAs, does it? Sine is, let's see, cos, no. So what in the world? Let me just jot this down though, and then we'll figure it out. That thing is hypotenuse over adjacent. But one of our SOHCAHTOAs is related to this, and I think Hayden knows which one, because is that what you want to tell us? Okay, so which one are we going to use? Which of the SOHCAHTOAs? That's right. That's right. So that's actually adjacent is over hypotenuse is cosine, so it's exactly what Hayden said, that this is going to be the secant. Very nice, very nice. So now let's just put this together. Let's see what's next. I guess we'll just go ahead and figure out our, oh, I know. It's always good to jot this down over here. 3 tangent of theta is equal to x. So that's going to clue us in to what's going to go here. And then 3 secant theta is equal to the radical. So that clues us into what goes there. I still need dx, but dx isn't that hard. So let's see, I'll pick another volunteer. Hold on, Hunter. Hunter, you know what dx is, don't you? You know the derivative of 3 tangent. Almost. 3 secant squared, that's right, yes. Okay, very good. So yeah, 3 secant squared. Remember, tangent, derivative of tangent is secant squared. The derivative of secant is secant tangent. Yeah, so it's easy to get those mixed up, but you're doing great. Okay, so there's my, oh, I should have a d theta there somewhere. Okay, so that, by the way, came from here. Okay, so let's see. I'm probably going to have to shrink my penmanship here in just a minute, but let's take those 3 things. There, I think I can see them all now. So the 3 things that are green over on the right, I'm going to take those and I'm going to make those substitutions here. So I have, I'll write this out, 3 tangent theta quantity cubed times 3 secant theta times 3 secant squared theta d theta. So just pause for a minute. Make sure you see where each of those things came from. This is a slow process. You got to take your time. That's why I can't give you more than one of these on an exam. Otherwise, that's all you would do. Okay. I'm going to clean this up. If you don't mind, I'm going to factor out all the 3's, combine the secants. So this is going to be 3 to the 5th, the same thing, 243 times the integral of tangent cubed times secant cubed. All right, now we've got to do some sort of substitution. And to do it, it would be nice if we could figure out what we're going to move over to be next to the d theta. So you remember just like up here, I kind of, where is it? Right there it is. Okay. So to go from here to here, I figured out that the sine of theta went with the d theta. And that's in fact what happened. Whoops. Sorry. That's in fact what happened with that substitution. So let's go down here and do the same thing. What do we put with d theta? There's a couple of different options, but only one of them is going to work. Thomas, do you have any guesses as to what you might put over there with the d theta? Ah, very good. Secant, tangent, tangent, secant, however you want to do it. Very good. So let me write it down, and then I'll explain why we want to do it this way. So whenever you have secants and tangents, you're either going to group together secant, tangent, d theta like this, or you're going to put secant squared d theta. The problem with secant squared is if I took two secants away from this, you'd only have one left, and I wouldn't be able to convert that one secant into tangents. You know, I suppose I could still do that. I could still convert it. It just would be ugly, and I don't want to deal with ugly. So this is a little bit better. And so that'll leave me. So when you do this way, you'll be left with two tangents and two secants. It's the two tangents that I'm really interested in. So let's just do one more step. Specifically, I can take those two tangents and change them into secant squared minus 1. I know, this is so overwhelming. It's so much work. But you know, the fact that it works is just amazing. Okay, so let's go up here. Let's see if I can clean things up. So let's see. Let's see up here. Oh, the substitution now. I think I can do it. U is equal to secant. Du is secant tangent d theta. So that was sort of the goal of rearranging things down there, is to get it to look like this. So let's make that substitution. I've got the 243 that's still lurking down there. This becomes u squared minus 1. This becomes u squared. This becomes du. Okay, so now things are easier. Let me do one more step, and then I'll see what sorts of questions you have. U to the 4th minus u squared du. We're doing great. So any issues with this? I know it's a lot to take in. So. All right, let's pound through. Now the rest of this I'm going to do pretty quickly because we've already done this sort of thing up here. So it's really not that surprising at this point, I don't think. 243 times we have u to the 5th over 5 minus u to the 3rd over 3. You all can do this part. Now we have to substitute back in. U is secant, so 243 times secant to the 5th and secant to the 3rd. And then a lot of times on the test, students will stop there because it feels like you're done, but no, we got another step. Remember, there's two layers of substitutions. And so we have to go all the way back and say, well, what does secant equal? Well, in terms of x, it looks to me like secant is this up here, radical 9 plus x squared over 3. What a nightmare. Okay, we can do this though. So then the final step, let me just change colors one more time. I guess I'll go back to black. Okay, so this final answer is going to be 243 times radical 9 plus x squared to the 5th over 5 times 243, because that's 3 to the 5th. And then this will be minus radical 9 plus x squared to the 3rd over 3 to the 3rd times 3, which is going to be 3 to the 4th, so 81. You'll have a similar situation with the previous problem where you're going to cancel some stuff, and then it ends up being, it looks similar to the answer we had up here, Yeah, be very similar, but some little minor changes because of the fact that we had a different substitution. Wow, so much. And one more, and then we're all done. Uh, but any other issues with this? This is a lot. It's a lot. What do you think, Red?
Now that you have purple and you have the fourth rule, how do you go from tangent square and secant square to secant square minus 1?
Ah, yes. So red is referring to this right here. Give me a sec. That turned into this. And so let me just go over here and remind everyone of our two identities. So this one, of course, we know. So bear with me if you don't mind for just a sec, because I know you know this one. And that can be rearranged so that you have something like sine squared theta is equal to 1 minus cosine squared, or vice versa. So the other one is this one, tangent, less well known, but it's also called a Pythagorean identity. And that can be rearranged to be tangent squared is equal to secant squared theta minus 1. So it's that one right there. This is what I did, is I took tangent squared and I just turned it into secant squared minus 1. So anything else? Other things that we need to deal with? So overwhelming, Michael? All right, yeah, I can. Maybe, okay, let's do that one a second time, and then we'll do the number 3. So let me just scroll over here to a clean one. So when I look at a problem like this, if I'm thinking that I might use trig substitution, oh, and I need to, I guess I should confess something about these 3 problems, and that is that I believe with all 3 of them, it is possible to do this using normal U substitution. So I just want to get that off my chest. So just confession. So it is possible to do this without trig substitution, but we're trying to learn about trig substitution. So I'm trying to come up with some easy problems that'll work. So if you really want to know how to do this without the trig functions, I could show you, but not now. Come to my office. Or you might be able to figure it yourself. Okay, so whenever I have a problem like this where I think maybe I'll be able to use substitution by trig functions, I take the radical. That's the keystone. That's the important part. So that radical, I need to be able to put that into my triangle somewhere. So to do it, I tear it apart and I say, okay, we have 3 squared and we have x squared. That feels like 2 pieces of the Pythagorean theorem. Specifically, 3 squared plus x squared is equal to the hypotenuse squared. And so when you take this thing apart, you say, okay, if I put an x here and a 3 here, and then let's just call this c for now, I would have c squared is equal to 3 squared plus x squared. So anyway, I take those squares and I think, okay, where can I put them on this triangle to make them make sense? And now that I've got that, you can probably see that c is going to be the square root of 9 plus x squared. And so that's why I put what I put where I put it. Now that's different from part number 1, and it's different from number 3. So let's take a look at number 3 to see how this is different. So whenever you have a minus, once again, I'm thinking maybe I can use trig substitution. And so the first thing I think of is, I think, how does this fit the Pythagorean theorem? So it's that radical that's the most important. This is x squared, of course, and this is 3 squared. And so I'm going to have an x somewhere. I'm going to have a 3 somewhere. The difference between this and number 2 is that I have a minus here instead of a plus. Whenever you have a minus, it should clue you in to the idea that maybe what you want to do is put x right there on the hypotenuse. So if the x is on the hypotenuse, then where would I would have to put the 3 on one of the other legs. So just pick one, but in general, it's this one will be the easier one. And if you pick the wrong one, you'll discover that when you start writing down the trig functions like we're about to do. So anyway, I'll put the 3 there, and then I think through, like if this was the Pythagorean theorem, what would that side be? Well, I know that x squared is going to equal 3 squared plus whatever that side is, squared. And then I can solve for b. So 3 squared is equal to b squared, which means b is equal to the square root of x squared minus 9. Sure enough, I've got one of my sides to equal that radical, which is what I wanted. So this is radical, x squared minus 9. So let me pause there because that really is the most important step. So as Michael was, I'm glad you brought this up, is that if you don't get that particular part of the setting up the triangle, the rest of it, yeah, you're not going to be able to get the rest. This is the keystone, the linchpin, if you will, of this type of solution. All right, so now the rest of this, I don't know if we want to do the whole thing, but let's see. So once you've got your sides labeled, the next step is to write down the trig functions. But notice that each time I wrote down trig functions, I always had the x over 3 and the radical over 3. Up here as well, x over 3, radical over 3. So let's do the same thing down here. Once I find it, I'll just shove it right in the middle here. I've got x over 3, and I've got the radical over 3. And I need to know which of the 6 trig functions each of those correspond to. Take a minute and see if you can work it out. You can use SOHCAHTOA, that is, sine is opposite over hypotenuse, and so on. And I'll bet you can at least identify one of these, if not both of them. So let's take a minute, see if you can do that. All right, Landon, what do you think? Do you want to do one or the other one? Do you have one of these? Really? Why don't we do the bottom one first? I know if you've got both of them that you're doing great. But what about that bottom one? What's that one? Tangent. Yeah, so that's one that's more familiar. You're like opposite over adjacent. Opposite over adjacent is tangent. Thank you so much, Landon. Let's see, I'll put that down. So that's the tangent. And then let's do the top one. The top one's a little bit harder, but if you've got the bottom one, the top one shouldn't be too much harder. Ben, did you get the top one? It is secant. Very good. So if you look at the top one, it's hypotenuse over adjacent. Oh, it's similar to the last one we did, right? Hypotenuse over adjacent is the opposite or the reciprocal of adjacent over hypotenuse. So that's going to be, yes, secant. Very nice. So that's secant. So the rest of this is pretty anodyne. Let's see if I can just get it started. I'm not going to do the whole thing, but I'll get the first level, if you will, of this substitution. So the x cubed, I guess I could do this. So x ends up being 3 secant. The radical ends up being 3 tangent. And then we're going to need to use this to get the derivative, the dx. Oh, that's something someone could do. That'll be fun. Maggie, you know the derivative of secant, don't you? Just start naming trig functions. You'll hit it. That's right. That's part of it. Anything else? That's right. Tangent, secant. Very good. Or secant tangent. I don't care how you say it. There it is. So very good. So derivative of secant is secant tangent. Okay, so now let's just put this all together. So going up here, bear with me as I try to copy everything down. So up here, that becomes the integral of 3 secant theta cubed times 3 tangent theta times 3 tangent theta secant theta d theta. I don't know if that needs any more explaining. Did I get everything? Now, you're going to think that every single problem like this has the number 243 in it. It's only because I wanted these all to look almost identical, the only difference being the thing under the radical. So that's why. It's not that there's anything magical about the number 243. But so let me clean this up just a bit. I'm not going to finish this one, just to warn you, but I want to just talk strategy. So this is secant to the 4th times tangent squared. So in keeping with our understanding of how to do trig functions like this, since there are an even number of secants, the right move to do is to take 2 of those and move them over so that they're with this the d theta. So I guess I'll do that. Secant squared. That leaves 2 of them over here and 2 tangents. The 243 goes along for the ride. Anyway, now I'm going to use that identity that secant squared is tangent squared plus 1. And then I'll do a substitution. U is equal to tangent. Du, it's right there, secant squared. So the rest of this is pretty straightforward. So what do you think? Any concerns? All right, we have. I want to do one more just to show you that these the 243 isn't some magical number. So let me go over here and find a good one. Hold on a minute. Oh, I love that one, but I'm going to skip it for now. Oh, this one's fun. Yeah, why not? Yeah, that one's a good one. Yeah, so let's take a look at this one. And as with the other ones that we did, we're not going to do this one in full. Sorry. I'm just going to copy this so that I can do it pretty quickly. I just want to get the first couple of steps in the substitution. So let me pull this over here. See, zoom out, paste it in. There we go. Oh, that's beautiful, isn't it? No, it's terrifying. That's what it is. It's horrible. Okay, so here's the way I would approach this. Before we get started, I'm going to rearrange this just slightly because there's no radical, is there? Well, there is, it's just hidden. So let me show you where the radical is. So this is the same as the integral from 0 to 3 radical 3 over 2 of x cubed over the square root of 4x squared plus 9 raised to the 3rd power. So double check that that makes sense just for a minute. So this is just algebraic manipulation. It's not even a manipulation, just a rewrite. Okay, so the next goal, the next step is to go over here. So this is the hardest part. Well, I don't know. There's so many hard parts for this, but this is the first hard part. Draw your triangle, put theta, right angle there. And the goal here is to have this somewhere. Now, before I move on, let's just point out what the building blocks are. 4x squared is 2x, quantity squared. And 9, of course, is 3 squared. You're probably sick of my 3, but there it is. So what I want you to do is label the 3 legs of this triangle. One of the legs will have 2x on it, or one of the sides. One side will have 3 on it, and one side will have that radical on it. See if you can get it figured out. I'll give you a minute. You can always lean over and look at what your friend has. All right, let's see what I did. So since there is a plus there, this clues me in to the thought that probably what I'm going to want to do is I'm going to want to have 2x over here and 3 here, or vice versa. And the reason is that if I use the Pythagorean theorem to figure out this side, I will do 2x squared plus 3 squared, and that'll give me that expression. And if you do the Pythagorean theorem, you'll find that this side is indeed 4x squared plus 9, well, the radical of that. And so that's going to be what this thing turns into. Let me just pause and see if you have any complaints, or if you say, well, could I do it this way? So if you have a different way to do it, it might be okay. Probably not, but it might be. So, okay, now that you've got that, there's a couple more things you need to do before we move on, before we let this one go by the wayside. One thing is you need to tell me what these things are. So 2x over 3, which trig function is that? And then the radical 4x squared plus 9 over 3. So notice that just like the other problems we did, I'd like to take the x over the number, and then I take the radical over the number, and I figure out which trig functions we're dealing with here. So I'll take a minute to work that out. I'll find a volunteer. Lewis, what do you think of that 2x over 3? Which one are you? That is the tangent. Very nice. So that's the tangent. And once you have the tangent there, you probably have a guess without even thinking about it what the next one is. But Braden, you want to tell me, don't you? What's that second one? That's the secant. Very good. So that one's that. So just to remind you, the tangent is opposite over adjacent. Secant is the reciprocal of cosine. Cosine would be this side over that, right? Adjacent over hypotenuse. This is hypotenuse over adjacent, so that's secant. Now that we've got that, we can do some rearranging. So let's see, this thing I would probably rewrite as 3/2 tangent is equal to x. This one I will rewrite as 3 secant is equal to the radical thing, 4x squared plus 9. And then one more just for fun, and that is, what's the derivative to get dx? Derivative of 3/2 tangent. And then we can finally actually set up what we're going to do, and then we won't finish this one because it is super. Oh yeah, Hayden, what? Okay, let me write that down. Let me pause. Oh, you got it now? Okay, but just in case, if you're struggling with what this all means, then let me write it down. Cosine, so let's write down exactly what Hayden said. The cosine he knows, and you all know, is adjacent over hypotenuse. So that's this. But what I'm more interested in is if I flip that fraction. And so we take that cosine and we say, wait a minute, I know that secant is 1 over cosine, which means those are reciprocals of one another. And so I can just take that fraction, flip it over, and I get my secant. So, which is exactly what you probably figured out when I scrolled. Anything else before I finish this one up? Well, do as much as I can. Okay, so derivative of tangent. So I'm doing the thing in the loop there, do the derivative, and I get secant squared. And now let's just take all of this. I just want to acknowledge that it is overwhelming. I know I've said that like 5 times. You're probably sick of it, but it is a lot of work. And that's why I only have 6 of these for Monday, and hopefully you did 2 of them for today. It's going to take some time. You're going to want to work with a friend. But anyway, let's get back to this. So this thing, I'm going to leave off the limits until the very end, which So x cubed is 3/2 tangent cubed. Then the radical cubed is 3 secant cubed. And then dx is 3/2 secant squared d theta. And I see that I left off a parenthesis. Okay, so I'm gonna highlight. I know that there we go. So x is this, which is this. Bear with me. The radical is this radical, which is this, turned into this. One more. Dx up here is over here, turned into this, which is right here. So I guess I guess this should have a d, whoops. This should have a d theta. There. Okay, so you see where everything came and where it went? Wow, it's kind of hard to read. So there they are. So let me just clean this up a bit and then we'll call it a day. So this is going to be this. Let's see, the threes. Let me just count threes. So this time we don't end up with 243. Check it out. I have 3 cubed, 27 in the numerator. 3 cubed, 27 in the denominator. They cancel. 3 here. So there's only going to be 3. And then for the 2's, I have 2 cubed, but it's on the bottom. So it's going to be 1 over 2 cubed, 1 over 8. And there's a 2 on the bottom here. So that's a total of 4 2's, which is 16. And then let's see, the tangent theta cubed, that came from the numerator, secant theta to the first in the denominator, because 3 secants down here, 2 secants up here, they're going to cancel. So that's what we're dealing with. Whew, that's hard. So what I would suggest, if I were going to do this, the next step I would take is I would pull out, because there's an odd number of tangents, I would pull out a secant tangent. I guess I'm doing it because we still have a couple of minutes left. So you have tangent cubed on the numerator. Tangent squared, because I said I was going to pull out a tangent here. And then you have secant in the denominator, but I'm going to pull out another secant, which I can't do unless I put an additional secant down there. So you see how I kind of used a little bit of magic? So you can see where the tangent came from, but if I'm going to put secant here, I better balance it. Then you can, now the rest of this is pretty straightforward. You have 3/16 times tangent is secant squared minus 1 secant squared, and then this is secant tangent d theta. Nice. Oh, it's too tempting. I gotta do it. So you end up with so u is equal to secant, du is secant tangent. Yeah, whatever. So this becomes du. This becomes 3/16 u squared minus 1 over u. Look at that. So simple. Squared. Sorry, u squared because secant squared. 3. I know I'm whipping through this. 1 minus 1 over u squared du. So this becomes 3/16 u minus, no plus, 1 over u plus c. Ooh, so good. 3/16 secant plus 1 over secant plus c. Look at this. I'm practically done. 3/16 times the radical over 3, was it? Plus 3 over the radical. There. I think that's what you'd end up with. Sorry, I skipped a bunch of steps. I know I went through that so quick, but the important stuff is being able to do this, where to go. The triangle is so essential. And then work your way through. I know I whipped through. Some of you are like, oh, I got lost back here before you even started going fast. But I'm pretty sure that if I put in my radical properly, that would be correct. So do your best with the homework. There's only 4 that you haven't done for today, or maybe 6 if you did nothing for today. And we'll pick up the pieces on Monday. On Monday, I will start actually keeping track of homework again. I'm back in business. So make sure you bring it. You don't have to rip it out of your paper or whatever. I'll come around and stamp it or give you a thumbs up. I'm going to stop the recording in case you want